All right, it's 5 o'clock. Oh man. Okay, hopefully like the audio isn't like too echoey, because I can definitely hear myself. But that's fine. So in today's recitation, we're just going to be covering antiderivatives. It's what we just did on Friday, I'm pretty sure. It's not too hard in general. It's just a pretty simple concept. It's basically just like doing derivative backwards of anything. So you'll learn sort of like future methods to sort of solve problems that deal with doing reverse like derivative rules. So right now we've only really learned like reverse power rule sort of, and then also kind of like, okay, if you have like a ln of x and that goes to 1 of x over x. So if you have 1 over x, it can just go back to ln of x, things like that. Or then also things like your trig functions as well. So just those sort of things. So you'll learn how to do like reverse chain rule and power rule soon. Or reverse power rule is more like a top 2 thing, whereas, reverse chain rule is actually something we'll get into in the coming weeks. It's something that I really enjoy doing. It's kind of fun, but it's also sort of difficult. So hopefully I can sort of like get through that with y'all in the future. But today we're just going to be doing like normal type power rule, like opposite power rule things. So I'm just going to go. No one's here, so I'm just going to go through some problems. I guess I cover everything. It'll probably be short. So let's start off with like a first one, just finding a pretty simple antiderivative. So if we have like f of x, say we have f of x equals 6 minus 3x plus 9, find f of x, where f of x equals, how do I say this? The derivative of f of x equals f of x, right? Okay. So how do we do this? Well, we sort of have to apply that mean like power of the opposite. This lighting is so bad. I don't know why it's. Yeah, that's even worse. Okay, is that like fine? Sort of. I don't know why the lighting like could not be more miserable in all of these rooms. Hopefully that like is okay. So let's say you have some function that's like, well, let's see about like what functions the power rule sort of like normally works for. So if you have some function like g of x equals, so it's some constant a of x, should be a of x to the power of n, g of x, the derivative of g of x is going to be defined as an and x n minus 1, right? So you take like n, you multiply down here, then you subtract 1 to it, right? Okay, so let's think about it like some function h of x, we can just say it's h of x equals ax of n. H of x, where it's similar to this, so the derivative of this is this, so the antiderivative of this function is this function. What do we do? So here we took whatever's sort of in front, so like this constant, and then, well, here what we did was we took this and brought it down, and then subtracted 1 from that. So here we sort of need to add 1 to this, and then divide this by that add 1, so that it can sort of like retain it's sort of like equality in a sense. So we can write like a over n plus 1 x n plus 1. Because if you think about it, n plus 1 times down here, it's going to be canceled out with that. We'll be left with a, and then up here it's going to be just n, because it's like n minus 1. So n plus 1 minus 1 is just n, right? So that works. So if we have this, 1 f of x, sort of use this methodology. So let's say we take x to the 6th, we get x to the 7th, And then our a value in this case would just be 1, right? So then we have to divide x to the 7th by 1, well, we have to multiply it by 1, which is a, over 7, because that's 6 plus 1, or n plus 1, right? So that's 1/7, right? So now if you can see that if you take the derivative of this part, 7 times 1 over 7 is just 1, and this would be x to the 6th. So that works. Next part, 3x. So you sort of like add 1 to the exponent of that variable, so that becomes x squared. Then you divide 3, or whatever that a value is, that constant value, right? Whatever the new exponent value is, that'll be 3/2. And this one is just 9x because you just add an x to it. There's always that plus c, because there could be some constant, right? Cool. So it's pretty simple. Okay. Now I want to try a bit of a harder one. Let's take some function f of x, 5 over cube root x fourth plus 2x root x. So whenever you see a complicated function like this, the best thing to do always is to make it so that you sort of have some kind of form where it's like ax n plus bx I, etc. So you have like some constant being multiplied by x to the power of something. So there are a couple different ways that we can sort of simplify this function into being into some kind of the following this form, right? So we know that, okay, you have 5 over the cube root of x to the 4th. Well, we can rewrite what's on the bottom here with just like the fraction thing, right? Where with a fractional exponent sort of. So we can sort of write it as 5 over x 4/3, because when you're doing exponents, the exponent goes on the top of the fraction, and then anything like that you're doing square root of it sort of goes on the bottom. You can add it, okay, well, let's say do the thinking here, 2x times x to the 1/2. Okay. So we can simplify this a little bit more. If you take some value on either side of a sort of like fraction, and you want to move it to the opposite side, you have to make its exponent negative sign. So we can change it like that. So 5x negative 4/3, that works fine. And then over here, we can just sort of add these exponents together. Just due to exponential rules, you get 2x to the 3/2, because this is like x first, right? Okay, cool. And now that we have it in this form, we can sort of, it's a lot easier to see how these like rules sort of play out when you're trying to take the antiderivative or something, right? Okay, so following sort of the same idea that we took from last time, let's see if we can figure this out. So what did I first do? I always added 1 to my exponent, right? So in this case, I'll probably say like, okay, f5 times something times x to the negative 1/3, right? Because negative 4/3 plus 1 is negative 1/3, okay? And then I want to divide this, this 5 by this new value on the bottom, right? So what that's going to end up looking like is, it's going to be a little confusing. It's actually going to be more like this. Okay, so the reason for that is because if you sort of take this a over n plus 1 idea, a is 5, right? Now our n plus 1, if this is our n, we add 1, so it's at negative 1/3 over right here, okay? And we sort of simplify this into just being 5 times negative 3, because this is more like 5 divided by 1/3, 5 times 3 over 1. Because dividing a fraction is the same time as same thing as multiplying by reciprocal, and this is 5 at negative 3, right? So what I always like to think of is that whenever I'm dealing with some kind of antiderivative where there's a exponent with a fraction, where there's a fraction in the exponent of some kind of variable, I like to think of it as, okay, I add 1, and then I just multiply it by the reciprocal of that. because it always sort of like flips over based on like this whole rule thing. So that's just sort of like an idea, and I can show you this one as well. So we'll simplify that later. We can add. So we're going to do the same thing. So like that's our A value times something times x. 3 halves plus 1 is 5 halves. And then we're going to multiply by the reciprocal of this, 2/5. And the reason for that again is 2 over 5 halves equals 2 times 2/5. Because it's sort of like, 2 over 1 over 5 halves equals 2 over 1 times 2/5. It really kind of like flips over, right? Okay. Cool. And now from here on out, we can basically just simplify. So 5 times -3 is -15. X to the -1/3 plus 4/5 x to the 5 halves. And then from here, we can sort of just write it out in our square root variant of this, I guess. So -15. This is going to go to the bottom because it's a negative exponent. And then it's going to be a cube root, nothing else in it, because it's got a 3 on the bottom. We can add 4. It's going to be 4 over times something over 5, because 5 is the only part that's on the bottom. It's, fraction is a negative exponent. And it's going to be square root of x to the 5th, because 5 is on the top and then 2 is on the bottom of that fraction in the exponent. So that's where we start. Cool. And then, this is our answer. This is our f of x. Also plus c. Sorry, also that. So always gotta remember that extra plus c. Cool. Something to definitely consider when you're sort of studying for all these things. I have a Quizlet that I'm probably gonna share with you guys that I used when I was trying to study for my midterm and my final, and I knew I had to memorize all these different antiderivatives and derivative rules. It's basically just like this table that I have written out, summarized. So all that makes, sort of sense. I mean, I don't know if it'll like go through and show you all the proofs for everything, but I'm sure if you wanted to find the answers online, like you're more than welcome to do that on your own time. But yeah, this is sort of like the what I showed you earlier. So you have x to the n plus 1 times 1 over n plus 1. Whereas, so kind of works. So cool. All right. Moving on. So I definitely recommend looking into to sort of getting just a lot of practice with doing these things, because antiderivatives and in the future integrals are a really important part of calculus, and I want to be able to have the muscle memory to just sort of do them naturally without really having to think about them. Especially with those like fractional exponent ones. Again, if you just kind of like add 1 to it and then multiply it by the new exponent's reciprocal, that is easily the best way to sort of like go about doing these things. At least how to think of them. So that is something to keep in mind for the future. So another part of these, how should I say? Another kind of type of problem that you'll often encounter are those initial value problems. Now, initial value problems allow you to specify what value of c you end up having in your final derivative or antiderivative function. So let's say you have a function f of x with properties, sorry guys, not a math major. F of x, the derivative of f of x equals sine of x plus 3, and f of 0 equals 1. So we want to find what f of x was. F of x. Okay, so let's just start out by writing out the derivative again. Derivative of f of x. And simply solving for that the original function as we sort of know how to do. So theoretically, how's it going? I was just going through some of the different problems with antiderivatives. That sort of work. I can't hear you. I think you're still muted. Can you hear me? That'd be really bad if you couldn't hear me. Maybe shut up. I hope it's picking it. Can you hear me at all? Is my microphone working? Oh, really? That's so rough. Okay. Hold on.
All right. Never mind. I actually hear you now. I think it might have just.
Okay, can you hear me now? Wait,
Yeah.
I just muted you. Hold on.
Okay.
Okay, can you hear me now? Can you talk?
Yeah.
Yeah. Okay, I can't hear you. Oh, wait. Okay, I might be working now. Can you speak? I can't hear you. Oh my goodness. I have this on mute. I have.
Okay. You still can't hear me?
Yeah, I can hear you now.
You can hear me now?
Yeah.
No.
It's just. Can you hear me? Yeah. Can you try to speak? Why can I not hear you? This is so weird.
Okay, hold on. Can you hear me now?
Yeah, we're good.
All right, perfect. Yeah, my Zoom audio
Okay.
is kind of variable. So
now I'm kind of worried that the entire first 15 minutes of my session didn't get recorded audio wise. So I think I might just start my content over if that's okay. I don't really have much to go through today. So I was just doing I don't know, I might just kind of just show you through how I did the problem rather than write it all out. Does that make sense? You're muted.
okay, I actually just have a question if that's okay.
Oh, no, that's fine.
Okay. Let me... okay, could I share my screen to show the problem?
Yeah.
Okay.
No, thank you.
All right, yeah, I'm just kind of stuck on yeah, there's some of it. I haven't really figured out.
Okay,
Yeah,
so it's probably pause.
yeah, but I'm actually confused because you can't apply is it Hospital's rule? Because it's oh, I actually think no, you can't because the bottom doesn't equal 0, it equals 8.
Well, if you plug in x0 for x there, that's gonna make the bottom 0.
Oh wait, okay, I was thinking okay, okay, wait, so then I just need to take the derivative of the top and bottom.
Yeah.
Okay. So then it would be e to the the derivative of e is 1 over x, right?
Oh yeah. So the derivative of e to the x is just e to the x itself.
Oh wait, okay, yeah, that's the natural line.
Yeah, the derivative of like ln x is 1 over x.
Okay, cool. All right. Okay, so then I took the second derivative, because then if I just took the derivative once, then it would be like e to the x minus 1 over 16x, which would still be like 0 over 0 or whatever.
After the first time?
Yeah.
Yeah, so you can do it again.
Okay, yeah. It's gonna be like 1 over 16, I guess.
Yeah.
Oh, wait. Yeah.
That sounds right.
Okay, cool.
Yeah. Does the rest of L'Hopital sort of make sense to you?
Yeah, I think I was just like struggling a little bit because I didn't really hold on, wait. Oh, sorry, actually I had another question on the same assignment. Okay, so for 7, yeah, so I found that I could use the rule, and then I took like the derivative one time, and then I got like cosine of x minus secant squared x over 3x squared.
So what's the derivative of tangent of x?
Is it not like secant? Wait. Yeah, it's secant squared x.
Okay.
Oh wait, but that's like sine over cosine, isn't it? Wait, no. That's like what? Okay, sorry, my mind's like. Yeah, the derivative of tangent of x is secant squared x.
Yeah, I can take your problem similar to this. I can take you through a problem similar to this. I can't do it exactly.
Okay. Yeah, that makes sense.
I'll take you through x. Okay. Just give me a sec. You can see this. I just made this x squared instead of x cubed because I'm lazy. So yeah, so if we plug 0 in for here, we get sine of 0, which is 0, right? Tangent of 0 is also 0. Because that's like y over x, right? And then that unit circle thing that I was really bad at explaining earlier, sort of here, like the y, that's like 0 over 1, because the x value here is 1 and its y value is 0. Does that make sense? Yeah, cool. And then x squared, that's just going to be 0 as well, right? So we have 0 minus 0 over 0, which is 0 over 0. So that means that we can use L'Hopital's to simplify it a little bit, right? Okay. So how do we want to go about doing this?
So you can just like take the derivative of like the numerator.
Yeah, the top and bottom parts, right? So we can get cosine of x for the top minus secant squared x, right? Over this 2x. Yeah. Okay. So what do we have here? So let's see if we can plug in and get something else. So plug in 0 to the bottom, that's going to be 0, which isn't really what we want. But let's plug in 0 at the top. Cosine of 0 is just 1, right? Same thing here, this x is 1. Secant squared of x, what's that? So secant goes to cosine. So that would mean that secant x is just 1 over cosine x, right? And we already decided that cosine of 0 is 1, so that would just be 1 over 1. So that's also 1. So then 1 minus 1 is 0, so that's 0 over 0. 0 over 0, so that means we can, again, use L'Hopital. So we're going to do the derivative again, right? So that's the derivative of negative, I'll just cosine.
So just be negative sine x.
Yeah, so we got negative sine x.
Yeah. And then like I was kind of confused about what to do here because it was like actually no, never mind. Yeah, so then it would be like minus secant squared x times tangent x.
So what is minus secant squared x really? What is it doing?
Like secant, like secant x times secant x, I guess.
Squared, right? Like this?
Yeah.
So what is this? So what kind of, this is kind of like, what is this sort of telling you? Like, how are you going to find the derivative of this?
Chain rule.
Yeah, chain rule, right?
Okay.
So you need to do something a little bit more different than just taking the derivative of secant, right? So how are you going to go about doing chain rule for this? Yeah, if you want to try to solve it, you're on your own before I try to sort of take a look at it.
Okay. Yeah, actually, yeah, that's actually I'll probably have to do that because I have like a meeting at 5:30. Okay. Wait, would it just be so the f term, would it be like x squared or negative x squared?
You can kind of think of the negative as being separate, and so you just like
Yeah.
at the very end. So I wouldn't really worry about it too much.
Okay.
So I could, yeah. So I would just think of like the negative as being totally apart from everything, and then just add it at the very end. Yeah, I think thinking of the outside function as being just x squared with a negative sign in front of it, and the inside function being secant x is sort of the way to go. And remember that your bottom denominator, your denominator term is different than mine. So you might need to do it a little bit differently.
Okay. Yeah, I actually have a meeting at 5:30, so I'm gonna have to go. But yeah, I'll definitely I'll just finish up this problem later.
Sounds good. Sounds good. Cool.
Okay.
The rest of it
Thank you.
of course.
What was that?
Yeah, the rest of it is pretty self-explanatory. Just make sure you're always taking the right derivatives and stuff.
Okay. All right. Thank you.
A good one. Okay, I'm just gonna finish the problem that we started there. I'm not gonna get the same answer as the homework, but this is me taking the derivative on the right Hopefully you guys can like hear me. So I sort of separated the negative secant x squared x into just being negative secant x and then all of that squared. So by chain rule, I took the 2 to the front and kept this sort of staying the same, which got me this part, and then I had to multiply it by the derivative of the inside function. The derivative of secant x is secant x tangent x, I'm like pretty sure. And then the secant x is just like combined. So right here, I would just get secant squared x tangent x. And so if I plug 0 into everywhere, this becomes 0. This becomes a 1 from right here, but this also becomes a 0. So it's 0 minus 0 over 2, which is just 0. And so in the actual problem, you'd have to do this again. So you'd have 3x on the bottom here, which would get you 0 over 0 again. Then you have to do another derivative, but that's just a little bit too like long-winded for me right now. So I'm not really gonna like bother with doing that. All right, just in case the audio is messed up from earlier, I'll just go over sort of antiderivatives really quickly. So let's say we have some function f of x and we want to find the derivative. Let's pretend it's already the derivative of some other function. We want to find that original function. So if we have some derivative function g of x, or I guess original function g of x, normally what we do to find its derivative is we sort of like subtract its exponent and you bring down the exponent and then subtract whatever that exponent was for that x. We have to multiply it by the original. We have to multiply the original exponent by the coefficient or constant that was already in front of the exponential x term. Whereas if we have some function at h of x and want to find its antiderivative, we instead add 1 to the exponent rather than taking it down, and then we divide by that added that new and added to exponent. So which would be that n plus 1 term, if that makes any sense. So say we have this original function x to the 6th. If we add 1 to its exponent and then divide by that new exponent, we would get 1/7. So if you take the derivative of just 1/7 times x to the 7th, you take 7 down here, 7 over 7 is 1, and then it's just x to the 6th. So you just have 3x, you add 1 to the exponent, so you get 2. And then you divide by the exponent, that new exponent, so you get -3/2. So you see that, you add 1, divide by it. This is just adding the x. You kind of have like an x to the 0 here. So you kind of pretend like it's like a new variable sort of, and then you add your constant because there could have been some constant in this function that in this like original function that it's where its derivative did not have this included. Gotten rid of. So C could be like any real number pretty much. That's a constant. The next example I went through dealt with some weird fractions and square roots. It's always best to put your function into the form of like axn x to the power of n without any fractions or square roots, just because then you can use the power rule or the reverse power rule in a sense super easily. So here what we did was we simplified each of the square roots just being powers of x. So here you took x to the 4th and cube root of that to just x to the power of 4/3. And we took the square root of x and just made it x to the power of 1/2. And then since it was sort of a denominator term for this 5 over x to the 4/3, we can just add a negative sign to that exponent on the bottom to make it sort of flip up to the top. Which allows us to get in that nice little x to the n, a of x to the n form. So like in here, phi is a, n is -4/3. Same thing with here. You can just use exponential rules to just multiply these two together or add the exponents together to get 3/2. Then from there, I went into a little bit of an example of how to sort of take a derivative, especially when you're dealing with antiderivative. Take an antiderivative when you're dealing with an exponents that have fractions in them, right? So say we have this x to the -4/3. Again, it's always best to write it out after having added 1 to the exponent. So I wrote out x to the -1/3, and then I multiplied that term by the reciprocal of that new exponent. And the reason for that is exactly what I have over here. So over here I have a over n plus 1. So a is our 5. N plus 1 is that -1/3, as we see here. So -4/3 plus 1 is -1/3. And then it's over. And so we have that a over n plus 1 form here. And then I basically just like sort of write it out and show why it's basically the same thing. And it's a very similar methodology here. So take 3 halves, add 1 to it to get 5 halves, multiply it by that newest reciprocal. The reason for that is because if we have this 5 halves, if we want to take the derivative of this part now, you multiply this down and the 5 cancels with the 5, the 2 on the bottom cancels with the 2 on the top, and then you're just left with this 2 out here. So it sort of makes sense. And then, yeah, I mean, from there on out, we sort of just simplify. We have a new added negative sign because of the -1/3. That's always important to remember. And then we sort of wrote it back out in our fractional and root form. So we added that cube root in and put it on the denominator of this term. And we made this into its square root as well. And then never forget to add c when you're dealing with indefinite and antiderivatives. Cool. So then I was going to go into like a bit of an initial value theorem thing. So initial value problems allow you to specify what that extra added constant c is for your problem. So say we have some for your original function after you've taken the antiderivative of some some function, right? So say we have an f of x with properties where the derivative of f of x is sine of x plus 3. And then when you plug 0 into f of x, you get 1 out. So we want to find what f of x is given these things. Okay, so the thing that we can do is just take the antiderivative of this derivative function, because then you just get the original function, right? So f of x, and this is just something that you sort of need to know. You just need to know the trig antiderivative rules. So you need to think about, okay, what trig function's derivative gets me sine of x? Well, I know that the derivative of sine of x is cosine of x, right? And I know that derivative of cosine of x is negative sine x. And I know that if I take the derivative of negative sine x, that gets me negative cosine x. And then finally, if I take the derivative of negative cosine x, that gets me sine x. So that's how I sort of think about it. It's like a little bit of like a circular pattern. Eventually gets me right back to where we started. So sine x comes from negative cosine of x. And then the plus 3, I mean, again, that's a pretty simple, just adding the x to it. And then you have the c, right? Okay. And so what I want to do is I want to find an f of x such that I know what this specific value of c is without it being just like a general constant, right? And I've been given the information to be able to do just that. So I know that if I plug in 0 for everywhere there's an x in this function, it will eventually equal 1, right? So all I have to do is set all of these, I have to set this side with 0 plugged in for x equal to 1. So negative cosine of 0 plus, I guess I can write it like this, plus 3, 0, plus c. And you'll see that after having plugged in 0 or whatever number you might be using for all of our x values, we're left with one variable, which lets us solve for it, right? So we have to sort of simplify what's the cosine of 0? Well, we know that 0, actually I did it right over here. 0 on the unit circle is just right over here on the x-axis, and that's just a distance of 1 to the right horizontally. And we know that cosine corresponds to that x distance, that horizontal movement. So the cosine of 0 is just 1, but because of the negative, we know that's going to be -1. 3 times 0 is 0 plus c. So now all we have to do is solve for c. We add 1 over to get 2 equals c. So therefore, our final function is negative cosine of x plus 3x plus 2. If we take the derivative of this, we can see that f prime of x, take the derivative of negative cosine x, that will be sine of x, and then plus 3. So it works out. Cool. Okay. I have one more problem to go over, and then that'll probably be it. Another initial value problem. So we want to find sorry, I'm just going through this problem that I have. I'm a little confused. Okay, that's weird. Okay, so I'm gonna write this out. So say we have some function whose double derivative is cosine theta. Theta is just like some arbitrary variable, doesn't really matter. And that g is 0 equals g of theta, or equals g of pi equals 0. So normally speaking, when you are trying to find the original function where you're going from the double derivative, where you're going from its double derivative, you need 2 different sort of like values in our output to find the 2 different constants that may sort of eventually end up as the double derivative. Sorry if that sounds confusing. Because if you take like one function in its derivative, so if you say like f prime of x, f double prime of x goes to f prime of x plus c. Well, f of x from that equals it goes to f prime of x plus cx, I guess, plus a d, some function, some value d, right? Because there could have been these 2 different values that could have been from in f of x to this one to this one. So that's why you need 2 different variables to plug in for this, which we'll see in a second. So if I want to find g of theta, I'm just going to do one derivative at a time. Trying to do multiple derivatives at a time will never lead to anything good. So, or one antiderivative at a time, I guess. So let's think about what this derivative might, this antiderivative might be, or what this derivative function might be. This single g prime of theta. So what's the antiderivative of cosine theta? Well, I can think about what function's derivative gives me cosine of theta. I know it's sine of theta, right? Because the derivative of sine is cosine. I need to add that constant, right? Okay, and this goes pretty well into g of theta. So from the last problem, I know that this is cosine of theta, right? Because the derivative of negative cosine theta is just sine theta. That's what I do here. And then I have to add that theta variable to this because I could have just taken the derivative of it and gotten rid of that. Right? And add another constant. Normally, actually, these are uppercase values. Sorry. And so now I need to plug in values to be able to solve for these things, right? And I know what they should be set equal to. That works out. So I can say that g of 0 equals 0 plus negative cosine 0 plus c times 0 plus d. So we got lucky here. This c is actually canceled out, so we're only be left with d to solve for. So z equals what's the, we need to just sort of simplify what cosine of 0 is. That's just 1, so it'll be -1 because of the negative sign in front. This becomes 0, so plus d, and then 1 equals d. Awesome. And now we use the other sort of like value that we can plug in that equals 0, alongside with our new found knowledge that we know what d is to find what c is. So I'll do g of pi equals 0 equals negative cosine pi plus c times pi plus 1 because of this. Okay, so 0 equals, what's the cosine of pi? Well, we know that it's sort of like this. Pi, the angle pi is all the way over here. That's in the -1 direction. It's in a just directly negative horizontal direction, and it's a length of 1 because we know that our units are closed a length of 1, right? So that means that a cosine corresponds to that x distance. So that means that since cosine of pi is -1, it being multiplied by this negative sign gives us just 1, plus c pi, because c times pi is that, plus another 1. So that'll give us 2 pi, -2 on the left equals c pi. So solving for c is -2 over pi equals c. So putting all of that together, we know that g of theta equals negative cosine theta. What is it? -2 pi. 2 theta. Yeah, -2 theta. I guess I can do -2 pi theta. Sorry, I'm like off like rock break, guys. Plus 1. And yeah, so that's how you do an initial value problem. It's basically just sort of like plugging in values to solve for specific constants that eventually got us to another problem. So when you get into like indefinite integrals, you'll always have to add your c at the end of that. So indefinite integrals, I mean like, okay, you have integral sign where f of x dx equals f of x plus c, right? Or you can sort of define the integral over some value, over some interval, such as a to b, f of x dx equals just f of x. To sort of solve for a and b, where you plug it in, or sorry, where you sort of plug these values in to get something specific, which you guys will see soon. Bradshaw will go over that. So this is like sort of difference between indefinite integral. It's not really specific. It's more like defining a family of functions, whereas family of functions that is sort of like bound by this, that is unbound by this constant with infinite possibilities. Whereas this indefinite integral is more represents like a number, such as an area or something like that, which you guys will get into in the future. Okay, so that's all. Sorry, I want to go over with. No one else is here, so I can't really take any questions. So I'm going to end the session. Thank you.